In this video, we'll go over Gabor transform threshold denoising with Fawav. It's quite a challenging denoising. First, we'll load a sound file. Let's look at its spectrogram. And as you can see, it's quite noisy, all these random gray pixels, a lot of static in there. The dark parts here correspond to the music. Let's listen to it. A lot of static. We'll also hear some low-pitch rumbling. First, Fawav's automatic denoiser. And we want to remove the low-pitch rumbling. So we'll take y greater than 200. There, do a high-pass filtering. And it removed a lot of the noise. We'll now invert. Let's listen to that. All of the static and high-pitch rumbling completely removed. The sound quality, though, is not the best. We thresholded actually at too high a standard deviation. We'll need to get a better estimate of the standard deviation. Oops, I got rid of the spectrogram. Let's get it back again. Now, a typical way of estimating standard deviation is to find a portion of the signal where there's just pure noise. Unfortunately, with this one, that is not possible. There is music playing all the time through the recording. So what we're going to do is isolate a portion of the spectrogram where we can see only noise there. I'm moving my mouse cursor around that area. You can find what the coordinates of that are by clicking View Cursor Coordinates. And so you trace the mouse around here till you found some coordinates that seem to be containing only noise. Now, I did that previously, and found this region here. So we're going to plot that function. G1 is the spectrogram, and then the inequalities will mark off a rectangle within that spectrogram. There. And that is, I think, pure noise. We will invert that now and get something we can estimate the standard deviation from. Now we'll change so that we're only over the interval, x interval specified above there in the spectrogram formula. And now just hit enter and it will replot. And then we do statistics. And we'll get the variance estimate here. Copy that. Now analysis calculator. We're going to let that copied value be V for variance. And then we do have to adjust the variance, so we're only using this portion of the frequencies there, and the highest frequency is 5, 12.5. So we're going to multiply by 5512.5 divided by 3263 minus 2680. And that'll give the adjusted variance. We want the standard deviation though for thresholding, so we'll take the square root there. And we get a standard deviation of that amount. Copy that. Go back up here, restore the noisy spectrogram. There's the denoiser. Now we'll put in the standard deviation. And we're going to do a garotte shrinkage. So we'll have here this part which causes the garotte shrinkage. Also we want a high pass again. And now we're set to apply this formula. That. Notice it has a lot more detail than previously. We invert. I get this result. Let's compare the audio from that with the original audio. And I think the thing although it does not work perfectly here, tremendous improvement has been accomplished. Here's first the original and then the denoising. Alright, so that is pretty successful. It's interesting that actually one can do a little bit more improvement on this. Now this is not based on theory but just empirical playing around, experimenting. I'm going to change the standard deviation to 150. And now it does appear like there's noise in there, but the garotte shrinkage, interestingly enough, damps down that noise when we invert. So now let's compare the original audio with this new synthesis. I think that's a pretty successful denoising considering how really noisy the original file was. That concludes this video. Thank you for watching.